US Physics Olympiad year 2023 USAPHO final round. Problem B1. Electric roulette. Consider a cylindrical solenoid with radius small r, length L much greater than small r, and n turns per unit length. It is made of one continuous wire, with the top connecting back to the bottom as shown at left. In the middle of the solenoid, part of the wire is replaced with the assembly shown at right. A uniform conducting rod of mass m and radius r is connected to the bottom half of the solenoid and is free to rotate about the solenoid's axis of symmetry. The end of the rod slides on a fixed conducting ring, which is attached to the top half of the solenoid. This assembly and the solenoid form one continuous conductor carrying total current I. First part. What is the inductance of this system? Assume that n r much greater than 1, so that the magnetic field produced by the current in the rod and the ring is negligible. Part B. When the rod is within a uniform vertical magnetic field B, find the torque it experiences in terms of I, B, and R. Part C. If the rod rotates with the angular velocity omega, the electrons inside have a tangential velocity. Find the electromotive force across the rod in terms of omega, B, and R. Now we will consider the dynamics of this system in some simple situations. For all the parts below, neglect energy losses due to friction, resistance, and radiation. Part D. First, suppose the system initially carries no current, and the entire system is inside a uniform external magnetic field B0, parallel to the axis of the solenoid. If the rod is given a small initial angular velocity, its angular velocity will oscillate in time. Find the period of these oscillations. Part E. Next, suppose there is no external magnetic field B0 equals 0 and at time t equals 0, the system carries current I0 and the rod has 0 angular velocity. First question. The rod's angular velocity omega as function of time approaches a value omega 0 after a long time. What is omega 0? Second question. Find omega t over omega 0 in terms of omega 0, t, n, and l. You may use the integrals on the reference sheet. Solution for problem B1. Part A. What is the inductance of this system? Assume n r much greater than 1, so that the magnetic field produced by the current in the rod and the ring is negligible. Solution. Magnetic field of solenoid, which is mu0 n I, so the flux through one turn of the solenoid is mu0 n I multiplied by cross-section area, which is pi r square. We have total n multiplied by L turns in total, so it means that total flux will be F1 multiplied by number of turns, which is NL. And finally, inductance is flux over current, which is mu0 n square pi r square L. That was solution for part A. Part B. When the rod is within a uniform vertical magnetic field B, find the torque it experienced in terms of I, B, and R. Solution. The torque is due to the Lorentz force on the current as it travels radially outward from the center of the disk towards its edge. If we take a small part of this rod on a distance s from center and length delta s, that will be delta tau equal negative delta f multiplied by s, which is negative bi delta s multiplied by s. Now we can integrate this result from 0 to r, which will give us total torque, which is negative 1/2 bi r square. The minus sign indicates that the torque tends to slow down the rotation when I is defined in the direction shown in the figure. This is consistent with the defining positive angular velocity and the torque by the right-hand rule. If you define it the other way around, this equation and the several others below would pick up sign flip. Since we didn't specify the sign convention in the problem text, either set of signs received full credit. That was solution for part B. Part C. If the rod rotates with the angular velocity omega, the electrons inside have a tangential velocity. Find the electromotive force across the rod in terms of omega, B, and R. Solution. By Faraday's law of electromagnetic induction, the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. In our case, magnetic field is constant, so we have to use formula EMF equal negative delta F over delta T, which is equal to negative B multiplied by delta A over delta T, where delta A is area of the small triangle which created by angle delta theta. So we have delta A equal 1/2 r squared delta theta, and finally EMF equal negative 1/2 omega B r squared. That was solution for part C. Next, now we will consider the dynamics of this system in some simple situations. For all the parts below, neglect energy losses due to friction, resistance, and radiation. Part D. First, suppose the system initially carries no current and the entire system is inside a uniform external magnetic field B0 parallel to the axis of the solenoid. If the rod is given a small initial angular velocity, its angular velocity will oscillate in time. Find the period of these oscillations. Solution. Here we can use results which we got in previous parts. Rotational motion of our rod, we have 1/3 m r squared multiplied by delta omega over delta t, which is angular acceleration, equal torque applied to this rod. We remember that torque was 1/2 B0 I r squared. Due to Kirchhoff's loop rule, we have EMF minus inductance L multiplied by delta I over delta t equals 0. Using expression for EMF, we have EMF equal negative 1/2 omega B r squared. It means that di over dt equal EMF over inductance L, which is after all this expression. From first two we have delta omega over delta t equal 3 over 2 B0 over m I. And now we can take a first derivative by time. from this expression, and using expression for delta I over delta t, we have second derivative by time from omega equal this expression or this expression. And finally we can see that second derivative from omega proportional to omega with a negative sign. This is exactly equation for simple harmonic motion, and from here we can find what is the period of oscillation of this omega. That will be period equal this one. That was solution for part D. Part E. Next, suppose there is no external magnetic field, B0 equals 0, and at time t equals 0, the system carries a current I0, and the rod has 0 angular velocity. First question. The rod's angular velocity, omega as function of t, approaches a value omega 0 after a long time. What is omega 0? Solution. Now, because external magnetic field is 0, we have to use magnetic field created by current I, which initially I0. That will be in solenoid mu0 and I. From a previous section we found that angular acceleration, which is delta omega over delta t, equal negative 3 over 2 b over m I. So using this expression for magnetic field B, we can write that because I square is positive, we have angular acceleration is always negative, and angular velocity will be increasing in negative direction and reach the final omega 0. From other hand, we had delta I over delta t equal 1 over 2 pi omega b square L. Now, using this expression for B, we got that delta I over delta t equal omega I divided by 2 pi and L. That because omega always negative, we have delta I over delta t is negative and the current always decreasing. Because we are not losing any energy, we have energy conservation. And because now we see that there are no oscillations, so it means that total energy equal mechanical energy for rotation plus energy of a magnetic field inside of the solenoid. And we have in any time this expression. And because final current is 0, we have this equation. Now we can divide our expression for energy conservation by right part. We will get equation equivalent to energy conservation. Omega square over omega 0 square plus I square over I0 square equal 1. Here we can use expression for inductivity. Inductivity for solenoid was mu0 n square pi r square L. Now, using this expression and this expression, we can find what is omega 0. Omega 0 will be this expression, which is a solution for question 1, part E. Question 2. Find omega t over omega 0 in terms of omega 0, t and L. Solution for question 2. Now we can use our energy conservation in this form. Also, we found that delta omega over delta t equal this expression through I square. So now we can use I square over I0 square in this form and put it to this expression, which will give us this one or this one. This is a typical differential equation. So this is the solution for differential equation, and finally we can express it in form of omega as a function of t over omega 0 equal hyperbolic tangent from negative omega 0 t over 2 pi ln. That was solution for question 2 part E, and here we finished discussion for problem B1.